one of my favorite parts about working at NVIDIA is that you get to work with absolutely cracked engineers like this guy. So I asked Kyle if he would sit down with me and answer some questions I have just about whole lot of stuff.
Yeah,
but
absolutely.
Yeah. So you were talking about model optimizations, and the way that you did it made it really clear that you know a lot more about model optimizations than I do. I guess when I say model optimizations, what are like the first few things that come to mind?
I wouldn't say I know more than you do
You know more
intuitively.
than, okay, you can take the title.
Okay. Well, when I think about model optimization, I think about a couple of things, right? There are user experience metrics that are really important. There are 3 total metrics. One is related to total cost of ownership, and 2 are related to the experience that the user has when interacting with the model. The 2 that are related with interacting with the model are the time to first token and the inter-token latency. Now, you as a user of ChatGPT or Claude or any API or platform to use LLMs are probably familiar with both intuitively, but haven't put a label to them. The time to first token is the time that it takes between the initial call to the LLM and the time until the first token is returned. Now, the second metric is the inter-token latency, which is in between tokens within the same stream, how long does it take to generate the next token? Intuitively, if you're experiencing this like in ChatGPT, the time to first token is the time where it takes for you the first token to be generated, and then the inter-token latency is just like the crawl, like how quickly it the text moves across the screen.
So if I understand correctly, you're kind of looking at model optimization as being 3 parts. One is essentially coming down to the optimizing the cost of total cost of ownership,
Which
or the cost
which
we haven't talked about, or the 2 optimizations of using the model. So it's optimizing on cost, optimizing on how long it takes before it starts spitting out characters, and then the optimization to getting your answer completed.
Yeah.
Interesting. So what are some optimizations that you do that essentially optimize the time to first token compared to the time to
inter-token latency? So that's a great question. The time of time to first token can be broken into a couple parts. One is just network latency, right? It's the time that it takes for your call to get to a server. And then the second component of time to first token is the time that it actually takes for that query, assuming that there's no queuing, assuming that you're not waiting in line, is the time that it takes that query to take your input and encode it into the KV cache. And this phase is generally called prefill. In prefill, you're essentially pre-populating these values that are important for calculating the attention, like the attention values for your and outputs for your transformer blocks. But you don't need you're not actually generating new tokens, right? You're just pre-populating this KV cache so that you're ready to go once you start actually creating tokens. Now, on the other side, right, when you're generating tokens, you're in something called the decoding phase. Right, in the decoding phase, you're using the pre-populated KV values in the KV cache, and you're continuing to generate new tokens auto-regressively and actually add on to the KV cache over time as you generate more tokens.
I see. So in a model that's maybe you're not fine-tuning, maybe you have a really clever prompt or a really big prompt. In a case like that, are you just going to experience essentially a longer time to first token because more is happening in the cache, but then the token speed is more indicative of the model and less so of like what you fine-tuned?
Well, you're going to have some costs in prefill. Remember that despite the fact that like you're paying for prefill and for time to first token, you're actually also paying for it for in decoding, because the amount you're basically doing attention across the entire sequence unless you're using sliding window attention. So you're actually calculating with values that are like behind you, right?
Oh, interesting. Okay.
So if you have like a very long initial prompt, you're still going to have, it's still going to get slower.
Yeah, I see.
Right.
Interesting.
Yeah.
How much does the context length impact the performance here? And at what point do you make a trade-off for how much you're stuffing in the context or moving into fine-tuning? Yeah.
Well, I think a lot of people are used to seeing like the numbers on like Llama 3.170B or 4.5B, and they say, oh, it has 128,000 context length. Let's just use it, right? Let's use all of it. And with this, I'd actually like to stress a little bit the importance of designing your inference systems to be application specific. So a good example of this is if you're building a model, right, and you have a very long context length, and you're creating an engine, an tensor TLM or some other compiler acceleration framework. That compiler is going to make decisions based on the context length, right? You're going to make decisions based on, like, oh, you have 128,000 tokens to either have as input or to generate, and you may choose different kernels to use, or kernels being the way that you actually do the operations within the neural network. You may choose different kernels to do your work, right? To perform the calculations that you need in order to do attention and to do the projection and everything else within the transformer block. What I'm trying to say is compiling and building for a specific sequence length often can net you advantages, even if you're not using, or like, especially if you're not using the full sequencing of the model, right? If you choose and you say, hey, my application only cares about the first 2,000 tokens, building something for that sequence length that's specific to that sequence length is going to be more performant than building something that's like general and can go up to 128,000.
Interesting. Wait, so why, if I compile the model focused on a smaller sequence, using only the amount of the context window that I'm actually going to use, why does that change the performance of the model, even if I'm never hitting the other parts of that context window?
So we talked about the KV cache, right? Which is that element that we mentioned that is used to pre-populate during prefill and is used during the attention calculations. It essentially comes down to the balance of memory that you're using on the GPU at any given time, right? Because you need memory for the KV cache, you need memory for the weights.
So if you're saying, if you can come in and say I only need a quarter of the context window that's available, then you essentially can stop reserving memory for what could go to the KV cache and instead optimize it for later parts of inference.
Yeah. Okay. Yeah. And there are also other interesting things, like a tensor TLM has something called chunked prefill, where you basically do everything chunkwise, and because of that, you can actually get away with using less memory. But
chunks meaning essentially like groups of tokens, right?
Groups of the KV.
Yeah.
But you essentially, if you are building something application specific, right, you should obviously choose the set of options that make the most sense for your application.
Interesting.
You're going to get a lot of perf that way.
Yeah, a lot of performance. It sounds like. So for, and I don't know if we're allowed to say names, but for companies that are building large models that have general use cases, what are they doing? Since it's very clear that they can't make optimizations on an like they don't know what the end user's application are, and they specifically want to cater to many, right?
Yeah. Keep in mind here that the applications that we're talking about like largely correlate to how long the inputs are and how many tokens you need to output, right? So when we say like something's application specific, it means that it's tuned to that input and output length.
Yeah.
But despite the fact that they can't optimize for a single input output sequence length, what you can do is system wide at a data center level, at a fleet of replicas level that you have if you have like many versions of the model.
Oh, interesting. So like if your prompt has, let's say 40% of the available context window, it will go to models that were trained for that specific size. And so maybe not trained, but rather inference engines that are built for a specific size. Yeah. And you can even get really crazy with it. You can use different GPUs for different sequence lengths. You can do things like dynamic routing, where if our short sequence length stuff is full, I can shoot it over to a long sequence length queue, and it'll be a little bit faster because it's going to get off of the queue, but it's going to be slower in aggregate. Or no, it's not slower in aggregate. It's going to be slower for the individual user, but still faster than waiting in the queue. You can do a bunch of crazy load balancing stuff like that. And you can also design for, as you mentioned, different sets of input sequencing and output sequencing. So in aggregate, you can kind of see like a number of applications that form like various areas of the joint distribution, the joint probability distribution of user queries. Let's say like there are a lot of users that are doing the chatbot mode, which has long input sequence length and short output sequence length. And we can group those all together. And if we get something that seems like a chatbot request, we route it to there. I see. Yeah. And so would it be fair to say that like every time I use my favorite chat LLM product.
API catalog.
Yeah, API catalog. That based on my query, it might be going to a different model, compiled differently for a different GPU.
It might be the same model represented differently.
Yeah. For something like a code gen use case, you typically have, or you're referencing a lot of different code paths, files. So do code gen models typically have, or are they typically compiled or optimized for much larger context windows, or?
Code generation is a very interesting one because there are many different ways that you can actually represent it. You can represent it on the single file level. You could represent it on the diff level if you wanted to. So I hesitate to say some like general thing, but if you are, for example, designing an application where you look at a lot of code and you're doing it zero shot, where you're not doing any retrieval, you're not doing RAG, you're just pasting in your entire code base and expecting the LM to work. If you're doing that, you care a lot about input sequence length, and you probably also care about output sequence length. If you're writing like long files, like if you ask it to like write a completely new long class to do something, it'll probably be a lot of tokens.
I see. That's super interesting. Oh yeah, learned a ton.
Fun.
Yeah.